I'm Yanliang. In this video abstract, I will introduce our work about the expansion of a quantum gas on the curved surface of a shell-shaped trap. What will happen if a curved surface is filled with a superfluid? In this case, very interesting topological effects will occur. For example, vortices come by pairs, and these vortices pairs have long-range correlations. The special physics of a superfluid on a closed surface have been studied recently in many theoretical works. The physics of a bubble-shaped BEC is under study aboard the International Space Station, where microgravity environment really helps to realize such a special geometry.
Here we report on an attempt to create a microgravity environment for atoms trapped onto a curved surface on Earth. In order to realize it, we should answer these two questions: how to generate a bubble trap and how can we compensate gravity? We will address them one by one. A bubble trap can be generated by dressing atoms with radiofrequency photons in a quadrupole magnetic field. Resonance happens when the Larmor frequency is equal to the RF dressing frequency. The resulting avoided crossing creates a very smooth potential. Therefore, the atoms are trapped on the resonant surface, which forms a bubble. However, due to gravity, the atoms scatter at the bottom of the bubble. Then, how to compensate gravity? This is a sad view of the isopotentials. The effective potential on the bubble surface is the sum of two terms, gravity and RF coupling amplitude. For circularly polarized RF field, an RF coupling amplitude on the surface is opposite to the gravitational gradient. This results in an effective anti-gravity force. By increasing the magnetic gradient, we can increase its magnitude to compensate gravity. We compare the experimental results and numerical simulations using the Gross-Bedawiewski equation. Here you can see the top and side view. As the anti-gravity force is increased, the atoms clamp on the bubble surface and fill the lower half of the ellipsoid surface. However, when we continue increasing the gradient, we obtain a non-expected ring located close to the equator of the bubble instead of filling the whole surface. The corresponding anti-gravity force is not large enough to pull atoms to the top of the bubble. How can we explain the formation of this ring? In our bubble trap, since the transverse trapping potential is not uniform on the surface, the potential is not separable at all. So, we have to take into account the effect of the transverse confinement in the potential. It enters as the zero-point energy of the radial ground state. This energy increases as the atoms climb onto the surface and becomes dominant near the north pole of the bubble. This provides a very effective barrier to repel the atoms and results in a ring shape. In conclusion, we present a novel gravity compensation mechanism that enables the controlled expansion of a superfluid on a curved surface. When gravity is fully compensated, we observe the formation of a ring-shaped trap stabilized by the zero-point energy of the radial confinement. Even if this method cannot realize a full-filled bubble geometry, it enables, for the first time, the study of two-dimensional atomic superfluids on a curved surface.